very often you can start with making a fractional factorial design with very, very few trials. And then if you have, for example, if you have a need and time and resources, you can improve the results by using Foldovers. So let's discuss that. Okay. Foldover is a way to make this so-called sequential improving. When you use the previous results, the results based on your previous design, and then just run a little bit extra experiments and make more reliable or more thorough results. Okay, what is a foldover? So let me show you, for example, a case study. So in this case, we, for example, we would like to find out how different effects, how different factors influence an ability of bicycle rider to climb a hill as fast as possible. So remember, we have a hill, you are a rider, and you would like to climb this hill on your bicycle as fast as possible. Okay, so which factors can influence this speed? Well, first of all, this seat position, is it up and down? Is dynamo machine on and off or off? The handlebars, up and down again, low gear or medium gear. Raincoat, if you have a raincoat on or off, okay, which is quite important in Denmark, for example, when it's quite often raining. Then breakfast, did you eat breakfast or not before you starting the riding? Then tires, if you have hard or soft tires. And finally, you have this is the response. It's a time to climb in a second, okay? So we have 7 effects. We have 7 factors. And then if you, for example, use a full factorial design, you need 128 trials. So if you use, for example, every day as a trial, you need more than 4 months, right? So what to do? Let's use as least trials as possible. So in this case, we are going to do everything in 8 trials instead of 128. Quite a big drop, right? So it means that we have only 3 main factors. And then the other 4 factors will be confounded with some interactions, right? So it means that this is the amount of confounded effects. And then it means that the design relation will be 2, 7, 7 minus 4. So this is our design. And then what will be the resolution of this design? We will discuss it later. Okay. Now look, this is my pattern. This is my design matrix. So you can see that the large letters A, B, C, D, E, F, G are our actually factors, and the small letters are the letters that corresponds to the effects and interactions, the main factors and interactions for the full factorial design with 3 factors. So you can see that, for example, small a is confounded with small b, and then you can see A, B, C as 3 main effects, right? Then you can see D is confounded with AB, A is confounded with AC, F is confounded with BC, and G is confounded with ABC. Okay, so this is our design matrix. Okay, now look, I ran it. So we made the experiments, and this is the effects we calculated. So these are main effects, and you can see interactions, right? So for example, we got an effect from A is 3.5. But in fact, it's effect from A plus effect from BD plus effect from CA and plus effect from FG. Okay, let me show you how I found this. Okay, so if we get back to this one, so you can see that, for example, D is confounded with AB, right? So it means that A is confounded with BD. So every time you see an effect from A, it is confounded with an effect from BD, right? Or for example, E is confounded with AC, right? But it means that A is confounded with EC. So every time we see an effect from A, it will be also confounded with EC. Then you can also see that ABC is confounded with G, right? But you can see that BC is the same as the effect from F, right? So it means that AF is confounded with G, or A is confounded with FG. Okay, so you can see that the main effect from A will be confounded with an effect or 3 effects from 3 2-factor interactions. It's BD, it's EC, and FG. So it means that the effect from A is in fact effect from A plus the effects from this EC plus BD and then plus FG. Okay, then we can think, what is the resolution when effect from 1 factor is confounded with interaction from 2 factors? Okay, so this is of course the resolution 3. So this is the resolution of our design. Okay. Now let's get back to the calculation. So these are effects, and you can see that the biggest effects we got are effects from B and effects from D, which is dynamo on off, and then D is a gear. You can see that you have also a positive effect from gear, right? But now look how we can improve these results. Of course, we can take B and D, which are the most important factors, and then, for example, make full factorial design with B and D only and look at the interactions and so on. But what if D also, for example, D has the biggest effect in this case, right? Maybe D also interacts with some other factors. Maybe D interacts with A, D interacts with F. We simply don't see it because our design was, the resolution of our design was too low. Can we do something to resolve all effects from D? Okay, to resolve all interactions from D. Yes, we can do that, and that's what actually Foldover does for us. What is Foldover? Foldover is when you take your original design metrics and then invert values from one column. In this case, we are going to do it for column D. Invert means pluses becomes minuses and minuses becomes pluses. So let me show you the Foldover matrix. So this is the another 8 experiments we have to run. So we have to ask a rider to climb the hill 8 times more. But in this case, we will use invert values for D. You can see the D now is confounded with minus AB instead of just AB. So this is a foldover. This is a foldover. What foldover will allow us to do foldover will allow us to see all effects from D, so including interactions. Why? Let me show you the calculations. First of all, this is now it's our full experiment. So we have two blocks. So this is block 1, which we just analyzed before. Now we need to run block 2. We have a blocking experiment. And then if you look at the difference between D in the first block and D in the second block, you can see that where you have plus in the first block, you have minus in the second block, and then vice versa. So D is a foldover now in the second set of experiments. Okay, so this is a foldover. Now, look, this is the results. So this is the first 8 runs, and this is the last 8 runs, so the second 8 runs. So you can see that you have, for example, effect of 10 here and effect of 25 here, while in the first run you had effect of 12 and 22.5. Okay, so this is not a problem. But now, look, the effects will be a little bit different now because D is like negative, right? So every time you have an interaction with BD, it will be minus. So see, we have minus here, you have minus here, you have minus here because D is negative now, right? So you have these values will be negative. You can just simply multiply to -1 here, right? Then you can see that you have minus here, you have minus here, you have minus here, and so on. How it helps us? It helps us very, very easily. Let's average the results. So let's, for example, take effect from A and average with effect from A prime, which is this one, right? Which is this one, where we use D as a foldover. So we have to take a sum and divide it to 2. So in this case, if we want to do that, we have to take 3.5 plus 0.7 and then divide it to 2, right? Which is 4.2 divided to 2, which is 2.1. So that's the average effect from A. It doesn't give us any additional information. It's still small. But now look, what do we have? We have A plus BD plus CE plus FG, right? Then we have minus these ones. So we have we have plus, of course, plus then A, then minus BD plus CE, then plus FG, right? Which gives us A plus CE plus FG. So we removed BD from this part. So it means that we eliminate interaction between A and BD. We'll eliminate this confounding between A and BD. So now BD is not confounded with this effect anymore. And then if you do these calculations, then if you continue this calculation, so this is what you will get, right? So this is the effect from A. We already seen this. This is the average effect from B. Again, we eliminated AD from this effect, right? This is effect from C. Again, the interaction with D eliminated. And then look, we have a clear effect from D. We don't have any interactions anymore. This is a clear effect from D. It's not confounded. It's not confounded with any interactions anymore. And then if you continue, you can see effect from BD, you can see effect from AD, DG, and so on. So you can see all effects where D is involved, interaction effects where D is involved. Okay. So by doing this simple foldover for one particular factor, you can actually resolve all effects, including two-factor interactions. And now we didn't get anything out of it. The effects are very small, right? But if we have any interaction of factor D with any other factors, we could clearly see that by using the foldover. So foldover is a way to improve your results, your fractional factorial design results, just by making another set of experiments. And then you will get also it's called blocking effect. That's what we are going to discuss in the next video. The idea is following: the average effect in the first set of experiment is 66.5. The average effect of the second set of experiment is 68.1, right? And this is the average for all experiments. The blocking effect, it's a difference between these two. So it means that you have a difference in your effect, some small systematic difference in your effects, but you can see it's 1.6, so it's about the same as the all noisy effect. So it means that we don't have any clear difference between these two sets of experiments, which is quite good, of course. And what else you can do? You can also do multi-column foldover. So the idea is the same, but now you make an inverse of all the factors, all the columns. In this case, you increase the resolution. So you remember we started with resolution 3 and we did 8 trials, 8 runs, right? So we can make another 8 trials with multi-column foldover, and it will simply increase the resolution to 4. So if your goal is not to see a clear effect from one factor, but you would like just to increase the resolution, then you can just use a multi-column foldover. Again, it's a good idea if you have some limited resources, so you cannot run all 16 trials at once. So you make a first set of experiment, and then depending on the results of the first set of experiment, you can think, okay, now probably we need to find resources for another 8 trials in order to see the effect.